Hi, everybody. Welcome back. And this is the fifth session of chemical kinetics. And the topic of discussion is going to be kinetics of first order reactions. So before proceeding, I would like to discuss the solutions to the homework questions that were given. So one among that was very easy. I have already written the solution. So let's begin. So the T half for A giving P, which is a zero order reaction, it's mentioned, is 20 minutes. This is the T half. We do know that T half and rate constant has got a relation. T half is equal to initial concentration by 2K. Initial concentration is also given. So you can rearrange, and as the questioner has asked us to report the answer in seconds, I have converted 20 minutes to seconds. So 20 minutes is equal to 20 into 60, 1200 seconds. That's all. There is a small unit conversion. So if I rearrange, the rate constant is going to be initial concentration 0.2 molar divided by 2 into T half is now 20 into 60 seconds. This is K. I'm not finding the value. Let that be. Now, integrated rate equation is initial concentration, which is 0.2. Final concentration, they have said it is 0.05. And that is equal to rate constant. We have got an expression into T. So I can rearrange and I get the final answer as T is equal to 1800 seconds. Okay, 1800 seconds. Now for zero order reactions, I would like to introduce a small trick which is going to save a lot of time. Okay, so I want everybody to note this down. Note. It's a very easy peasy trick. And this is applicable only for zero order reactions. Okay, so please note down in zero order reactions, equal amount of reactant drops in equal intervals of time. I'll explain. Intervals of time. Please note down. Equal amounts drop in equal intervals. That's all. Okay. Now, as an example, let's say that I started with 100 units of any concentration of the reactant. Okay. And at T is equal to, let's say 3 minutes. Okay. Whatever it is, whether it is T half, whether it is T, whatever. There is some time interval that is 3 minutes, after which 100 becomes 80. That means there is a drop of 20 units after 3 minutes initially. And this drop will be consistent. Same amount, for example, after 3 minutes again. That is now it is a total of 6 minutes, okay? Initially from 0, now 6 minutes have passed. So this is the second 3 minutes. Again, the same amount will drop, which is 60. The next 3 minutes, same amount. Oh, sorry. 3 minutes passed away, same units, that is minus 20, it's going to reach 40. Okay. Again, next 3 minutes, it will become 20. And again, 3 minutes, it reaches 0. So whatever time is given to you, let's say in 15 minutes, this is reduced by 50. So how much amount is reduced? 50 units. In what time? In 15 minutes. So what will happen in the next 15 minutes? Again, the same amount. That is, initially it was 50 units. Again, the same unit will disappear, which means it will become 0. Okay. So this is a shortcut which is applicable only to zero order reactions, and you can use the same shortcut to solve this as well. Let's see how. Okay, what is the question given? The question says that, I'll just note it down, that T is equal to 1200 seconds. What does the question say? It says that the half-life is 20 minutes. Half-life is 20 minutes is what is given. So we start with 0.2 molar in 20 minutes, right? Twenty minutes. So half-life means whatever concentration we have, the exact half is reduced. Correct? In 20 minutes, the exact half is reduced. Or the initial concentration becomes 50% of the initial, which is 0.1 molar. So there is a drop by 0.1 molar in 20 minutes. So if I equally divide, what is the rule? Equal amount drops in equal intervals of time. So if I say in 20 minutes of 0.1, amount is reduced, 0.1 molar is reduced, I can say that in 10 minutes, let's say I have 10 minutes, which is half the time, half the amount will be reduced, correct? What is half of 0.1? 0.05. That much is reduced, sorry. That much is reduced, which is 0.15. Equal amounts in equal intervals of time. Equal amounts in equal intervals of time. I took by 2 over here. Here also it will become by 2. That's all. So 10 minutes minus 0.05 is reduced. Next 10 minutes, again, minus 0.05 is reduced. Now it becomes 0.1 molar. And in the next 10 minutes, again, minus 0.05 molar is reduced and it becomes minus 0.05 molar finally. And that is what we want. How much time did it take? 10 plus 10 plus 10, 30 minutes. And 30 minutes is equal to how many seconds? 30 into 60, which is equal to 1800 seconds. It's okay if you're not comfortable with this. It's totally okay if you're not comfortable with this. If you're okay with the integrated rate equation, you can go for that. If you're confident enough to apply the shortcut, you can do that as well. It will save a lot of time. Okay. All right. Next question. Very important. Choose the correct plot for log T half versus log K for a zero order reaction was the question. So let's write down the equation. We all know that K is equal to, or T half. We need it in terms of T half. T half is equal to initial concentration by 2K. Now what they have given is log T half. So of course we'll have to take logarithms on both the sides. So it becomes log T half is equal to log of A by B. Correct? Log of A naught by 2K. And what is log A by B? That is equal to log A minus log B. If I apply that, log of A naught minus log 2K. Okay. Just a second. Okay, there was a mistake in the question. It's not, it's log T half versus log A. I'm sorry. Okay, log A. It's not K, it's A. Fine. Okay. All right. So this is of the form we have the y term along y-axis log t half, and we have the x term as well, correct, along the x-axis. And this is of the form y is equal to mx plus c. So m slope, the coefficient is 1, and this is minus c. Okay. Now there are three options given. See, all these are correct, and the correct answer is option B. I'll explain how. If, okay, I'll explain how. So here in the first graph, you can see that the line is passing through 0, which means the intercept is equal to 0 over here. Which means this term as a whole has become 0, and that is possible. How? If log 2k is equal to 0, or if I can say that the value of 2k is equal to 1, or in other words, I can say that the rate constant is 1 by 2 units. In the respective units, so maybe T half is in seconds, initial concentration is in molar. If K is equal to 1 by 2 molar, this is a zero order reaction, molar per second, then our intercept is going to be 0 because log 2K is going to be 0, and you will get a graph where the line passes through the intercept. Right. Now option B is also possible. Option B is a case where the intercept is a positive value. The intercept is a positive value. That is also possible. How? You can see that this is minus, and at any point, if log 2k is also a negative value, when will logarithm value become negative? When 2k is less than 1, correct? All the values of log less than 1, for example, log 0.1, 0.01, everything is negative. So you have negative into a negative value, which makes the intercept positive. And you can get a graph like this, a line like this. And in case C, if I extend, I can see that this is touching the negative y-axis and it has got a negative intercept. The intercept is negative, even that is possible. How is that possible? If I put log 2k should be positive. If log 2k is positive, there is a negative over here, which makes the intercept negative, and 2k is greater than 1. So all these cases are possible depending upon the value of the rate constant. Okay, so please note the x-axis is not log k, it's log a0. Sorry. Yeah. All right. So correct one is option D. Option D. Let's move to the next one. Kinetics of first order reaction. Kinetics of first order reaction. Okay, so let's start. Let's say that we have a reaction where again A is becoming P products. As we know that the initial concentration is represented as A naught, where product is not being formed. And at some time T, X amount is reacted or consumed, and it appears as the product, X. Being the first order reaction, N is equal to 1, our expression would be rate is equal to rate constant into concentration of A to the power 1. This is the experimental rate. Theoretical rate can also be written as minus d concentration of A by dt, which is also equal to R. In terms of reactant or in terms of product, I can write it as dP by dt. Correct. Now, this is in terms of A, this is also in terms of A, and both of these notate rates. I can compare the experimental rate and the theoretical rate, and upon comparing, what do I get? I get it as minus dA by dt is equal to rate constant concentration of A to the power 1. Okay. Now, before moving further, let's plot a graph. Plot a graph between rate of the reaction and concentration for a first order reaction. We know that rate is equal to rate constant into concentration of A. We have rate along the y-axis. We have A along the x-axis, and this is simply of the form y is equal to mx. There is no intercept. Intercept value is 0, which means it's going to be a straight line which passes through 0. Easy. And what would be the slope? K, rate constant. All right. So once we have compared the theoretical and the experimental rate, so we have already written, if you want to repeat, please write it again. This is the theoretical rate. This is the experimental rate. We have to integrate. Why do we integrate? We have to know the expression for a wider time interval. That is the meaning of integration, the physical meaning of integration. So when you integrate this, so you integrate over here, you integrate over here. Correct? So before integration, let's rearrange. Let's bring the A terms to one side and let's take the T terms to the other side. So if I rearrange, what I get is I bring the concentration term to the left. I take T and the negative term to the other side and I integrate. So we start from T is equal to 0 to a final time T. And at T is equal to 0, our concentration is going to be A naught. At final time, our concentration is going to be just A after X amount has been consumed. Right? Now, what is it that we should know? We should know that integral of 1 by x dx is ln x. What do we have over here? We have 1 by a dA. Instead of x, we have a. So this is going to be ln a, natural log, ln, okay? Ln a from the limits a naught to a, and integral of dt, as we discussed earlier, very easy. It is minus kt from the limits 0 to t. Let's put the limits. How do you put the limits? Upper limit minus lower limit. Correct? So what do we get? Ln a minus ln a naught is equal to minus k t minus 0. T minus 0 is t, so I'll write it as minus kt. Now if I take the minus to the other side, what will it become? It will become ln a0 minus ln a equal to kt. Correct. Ln a0 minus ln a equal to kt. So this is the first form of the integrated rate equation for a first order reaction. Let's plot a graph. What if I have to plot a graph between natural logarithm? So ln is the natural logarithm, okay? It's different from log. Natural logarithm is not equal to log. Ln is not equal to log. Okay, ln is 2.303 times log. For example, I have ln x. Ln x is equal to 2.303 times log x. Don't make mistakes. Okay, so if let's say that I want to plot a graph between ln a versus t. How will you rearrange this equation? You have to rearrange this equation in such a manner that ln a stays on the left, y, and t comes as x. Correct. So I'll take this equation. I'll take this equation and I'll bring this ln a0 to the right. Let's see how it will look. If I take this equation, let's say this is 1 and let's say this is 2. I'll rearrange 1. I'll rearrange 1, or you can rearrange 2 as well, whatever is easier for you. Ln a, I'll keep it on the left because that is my y-axis, is equal to this minus ln a0 on coming to the right will become plus ln a0 minus kt. That's it. Correct? So I get a graph where my y-axis is ln A, my x-axis is t, and I have got a negative slope, and my intercept is ln A0, which is positive. How will my graph look like? It will be like this. Correct? So it will start with ln A0 and has got a slope of how much? Has got a slope of minus k. It will touch the x-axis. I'll explain what this term is. It will touch, okay? You can extend the line until it touches. It will touch. Okay. Fine. Now we have written the expression in terms of ln. You can write it in terms of log as well. What is the relation? Ln x is 2.303 times log x. Correct? So you can change to log. It will become 2 point or yeah, okay, let's do. Or wait, before going to that, we can rearrange over here itself. Ln A minus ln B, you know, is ln A by B. So this is ln A naught by A is equal to KT. From the relation, ln A minus ln B is equal to ln A by B. When this is possible. Now the same things what we have written in natural logarithm can be written in just log. Log. How will you do? Let's name it as equation number 3. Now, how will you convert equation number 2 to logarithm? You multiply it with 2.303. That's all. Correct? So it becomes 2.303 log A naught minus 2.303 log A is equal to K3. Sorry, KT. This is equation number 4. 2.303 is common. I'll take that out. And again, we have log A minus log B. So upon rearranging, what do I get? Log A naught by A is equal to KT by 2.303. Easy. Easy. Okay. This is going to be my equation number 5. Be careful. Be careful. Let's say that I want to plot a graph between log of A versus T. Okay. From equation, let's say 4. I want to plot log of A versus T. So earlier what we did was ln, which is natural logarithm. Here what I'm writing is log. So what are the changes? So let's take 4 and rearrange, okay? In 4, 2.303 is common, correct? So I'll take that outside. So it become 2.303 log of A0 minus log of A is equal to KT. This is what I have. I'll take 2.303 to the other side. Log of A0 minus log of A is equal to KT by 2.303. Now I want log A along Y. So that should be on one side. So I'll take log A to the right and I'll bring this one to the left. So it will become log A0 minus KT by 2.303 is equal to log A. Now our form is correct. This is along Y and this is along X. This is of the form Y is equal to mx plus c, where the intercept is positive and it is log A0. We have got a negative slope, but understand that the negative slope is minus k by 2.303. Pay attention. Can you see the difference? When it was ln A versus t, our slope was just minus k. But when it is log A versus t, it is minus k by 2.303. Many students have made mistakes over here because they forgot the conversion and it got mixed up. And you get a, in the exam, you get options where both of these are there. Answer corresponding to minus k and answer corresponding to minus k minus k by 2.303. So don't get confused. Pay attention. Focus. All right. Now I'll take equation number 6, another equation that you need, and it was asked in June 2025 as well, a variation. So I'll take equation number 3. I'll take equation number 3 to derive equation number 6. Okay. So what do we know? We know that ln A naught by A is equal to KT. Now, if I take the reciprocal over here, for example, if I say that ln x is equal to y, if I take a reciprocal over here, which is ln 1 by x, it's going to become, the right hand side is going to become minus y. That is what I'm going to do over here as well, okay? So I'll take the reciprocal over here in such a way that now a comes on the top, a naught goes to the bottom. All I have to do is, I have to put a negative on the right hand side. These are all basic mathematical operations. So it becomes minus kt. Now I want to remove this ln. In order to remove this natural logarithm, I need to put exponential. Why? Because let's say I have ln x is equal to y. Taking anti-ln on both sides looks like x is equal to e to the power y. This is how it looks. Taking anti-ln on both sides. Okay. So if I take anti-lns on both sides, it becomes a by a naught is equal to e to the power minus kt. And if I rearrange, final concentration is equal to initial concentration e to the power minus kt. Equation number 6. Equation number 6. Okay. Based on equation number 6, let's plot a graph. Let's say that I want to plot A versus T. How is it related? A versus T. How is it related? It is related exponentially, negative exponential it is. And any graph of the form y is equal to e to the power minus x. That's how it is, correct? This is y, and you have some coefficient e to the power minus x. That is how it is. Any graph of this type shows a negative exponential degrade like this, and it never touches. Note, it never touches the x-axis. Can write a note over here, it never touches. So this is going to be the initial concentration A naught, and it will degrade exponentially. It will touch the y-axis, it won't touch the x-axis. It will touch the y-axis, it won't touch the x-axis. So this is how the graph for equation number 6 looks like. Similarly, they can also ask you of the patterns of how rate of the reaction versus time looks like. So initially what we plotted was rate versus concentration. Pay attention, which is R is equal to Ka. Here what they are asking is rate versus time. So we need to come to an equation where there is rate and where there is time. How will you come? So you know that R is equal to K into concentration of A. From equation number 6, you know that A is A naught e to the power minus KT. That's it. How are they related? We have R along Y. We have T along X. This is also of the form Y is equal to some constant into e to the power minus EX. Again, it's going to be a exponential degrade where it's not going to touch the y-axis. Very important. Having the ability to understand the graphs, to interpret the graphs, to draw the graphs once you have the grasp on formula. Very important. Okay? So this point over here, saying that it will never touch, okay, is very important. I'll take up this point after a while. This won't touch. So in zero order reaction, we said that it will touch. Here it won't touch. Very important. Okay. Calculate the half-life, please. Calculate the half-life. You can take any equations. Let's say you take equation number 3. Half-life. What is half-life? Half-life of first order reactions. Half-life is the time at which the initial concentration reduces by 50%. Correct? Which means if it was initially A naught, it will become A naught by 2. It is reduced to 50%. Correct. So our equation number 3 is initial concentration, natural log divided by A is equal to KT. What will happen at T half? At T half, this will become 1 by K. I took K to the other side. Ln of initial concentration won't change. Final concentration will become A naught by 2. Correct? So final concentration is A naught by 2. A naught and A naught gets cancelled. So this becomes 1 by K ln 2 is equal to T half. And the value of ln 2 is a constant, which is 0.693 by K T half. Very important. T half is equal to 0.693 by K. T half of a first order reaction is equal to 0.693 by K. Very important. You get a lot of questions from half-lives, half-time, integrated rate equations, etc. Now, if you can recall, the T half for a zero order reaction was initial concentration by 2K. Now, the T half for the first order reaction, you have got it as 0.693 by K, which means for the first order reaction, there is no dependence on the initial concentration. Is there a term of initial concentration? No. So if people ask you to plot a graph between t half versus the initial concentration, it has no dependency. It's independent and it's going to be a straight line. It's independent and it's going to be a straight line. While in zero order reaction, we did see that they have a linear dependence. And if you plot t half versus a naught, you will get a straight line having a slope of 2k. Here, it is independent. Okay. Find water life as well. Please find water life as well. Easy. Quarter life is the time required to reduce the initial concentration to 25%. Correct? So what is our equation? It is ln A0 by final concentration is equal to KT. At quarter life, this becomes, initial concentration won't change. Final concentration is going to be A naught by 4. Correct. A naught gets cancelled, which is going to be equal to ln 4 by, if I take k to the side, ln 4 by k equal to P1 by 4. Very easy. That's it. You can calculate the value and you can write if you want. That's it. Okay. Next thing, completion time. Completion time, T100 or tau. So it is the concentration, or it is the time required for the final concentration to be 0. Correct? That is ln A naught by A is equal to KT, and at KT 100%, initial concentration tau won't change. Final concentration is 0, and any number divided by 0 is infinity, and infinity divided by any constant is also infinity, or the time required for the completion of reactions which proceed with first order kinetics is infinity. That is why when we plotted a graph over here, A versus T, I'll paste it over here again. See, when we plotted A versus T, we said that there is an exponential degrade and it will never touch the x-axis. What happens if it touches the x-axis? Any point on the x-axis, we do know that the concentration of A is 0, y-axis is 0, and there is no time at which this y-axis becomes 0 when concentration of A becomes 0. That is the speciality of first order kinetics, and hence tau is equal to infinity. So this point, this highlighted region, which states that the line never touches the x-axis, means that the time required for the completion is infinity. Infinity, and the best example for this is radioactive decay. Radioactive decay is very important because in exams, they might not mention that it is a first order kinetics. They might just say that it's a radioactive decay. So you should have an understanding that whatever the radioactive decay is, it's always going to be following the first order kinetics. Okay? All right. Now for first order kinetics, there is another term called average life as well. Average life. Average life, you can write it as T average. Okay. Note down, it is the time at which time at which concentration of the reactant is 1 by E times of its initial value. Okay. So let's take the equation. We have ln of A naught by A is equal to KT. Write it each and every time so that it gets imprinted. Write it. Okay. Now at T average, it was said that the final concentration becomes 1 by E times of the initial, correct? 1 by E times of the initial value. And if I take K to the other side, this becomes like this. Yeah. So A naught gets cancelled. So it is ln E by K, which is equal to T average. And what is the value of ln E? Ln E is equal to 1. Okay. And log 10 is also equal to 1. Have this. So T average is equal to 1 by K. T average is equal to 1 by K. So when do you call it a T average? The time when the initial concentration has become 1 by E times of the initial value. 1 by E times of the initial value. Okay. All right. Now, having known this relation ln E is equal to 1, I will like to again revise one of the graphs which we had drawn, this one. Okay. This has not been asked, but they can ask. I said that when you draw just A versus T, it won't touch the x-axis. But if you plot ln A versus T, it will touch. Meaning, there can be a point where ln A is equal to 0. Correct? There can be a point where ln A is equal to 0. And what is that point? It is the point where concentration of A is equal to 1 by E. Just 1 by E. So let's see, which is, let's say ln A is equal to 0. Now I have put, oh, just a second. Okay, sorry. Okay, fine. So there can be a point where ln A can be equal to 0. Understand that ln A being 0 is not same as A being 0. Have this understanding. Okay? Have this understanding that ln A being 0 is not the same as A being 0. So there can be a point where ln A is equal to 0. That is possible. Okay. So when you plot a graph between ln A versus T, it will touch the x-axis. But if you just draw A versus T, that's not going to touch because A will never become 0 in a zero order reaction, but ln A can become 0. ln A can be considered. Okay. All right. Just give me 2 seconds. Okay. Yeah, that's it. Fine. So this is a point where uh, the ln of the concentration can be equal to 0. Fine. Okay, so let's take some questions. Question. Um, Graphical question. Question number 15 it is. Question number 15. Choose the correct plot. Choose the correct plot for ln A naught by concentration of A versus T for first order reactions. For first order reactions. Okay. I think it's better that I just a second. Okay, so what we have is log A naught by A versus T. There are 4 options. The options look like this. One is a straight line. The other one is exponentially increasing. Next one is exponentially decreasing. And the last one is decreasing straight line. Okay, very easy. We have been writing this for a while, that ln A0 by A is equal to KT. So we have A0 by A along Y, and you have T along X. Okay, so this is of the form Y is equal to mx. Slope is positive. It is a linear trend. So correct one is option A. Okay, for this, it's option A. Easy. Next question. Question number 16. This will be your homework. Plot a graph. Plotting a graph. That's a statement type graphical question. Okay. For ln A by A naught versus T for first order reaction. For first order reaction. This was asked in June 2014. Okay, option A. It's going to be a straight line with positive slope passing through origin. It will be a straight line with positive slope passing through origin. Okay. Option B, it's going to be a straight line with a negative slope passing through origin. Option C, exponential curve asymptotic to time axis. Time axis. Option D, exponential curve asymptotic to ln of A by A naught. Okay, so this is going to be a homework question. Do try it out. Question number 17. For a given reaction, of first order, it takes 20 minutes for the concentration to drop from 1 molar to 0.6 molar. The time required for the concentration to drop from 0.6 to 0.6 molar is option A, greater than 20 minutes. Option B, less than 20 minutes. Option C, 20 minutes. Option D, 40 minutes. Easy question. So what is given? It was given that for the concentration drop from 1 to 0.6, it takes 20 minutes. Correct? So let's use the equation. K is equal to, we know the time, right? 1 by T ln of initial concentration by final concentration is our equation. So you can use this equation, use the calculator. 1 by 20 minutes into ln of initial concentration was 1 molar, final concentration is going to be 0.6 molar. Molar gets cancelled. Okay, you can substitute the values, find the equation, and you will get that K is equal to 0.0255 per minute. It's a first order reaction, so the unit is just going to be per time. Now, what is the question? You know K. You have to find the time for the concentration to decrease from 0.6 to 0.36. Now the concentrations have changed. So we have to find the time at which 1 by K you already know. Initial concentration is 0.6 and the time required to drop it to 0.36. That's all. You have to put this value of 0.0255 over here. Take your calculator, solve it, and you will get it exactly as 20 minutes. 20 minutes, option C. Very easy question. Option C. Okay. Last question of the session, very important. Question number 18. Question number 18. Okay. Important. Asked in June 2025. The rate law for the reaction. Rate law for the reaction N2O2, which is in gaseous state, becoming 2NO in gaseous state, is first order with respect to N2O2. Okay. If the initial concentration, of N2O2 is 1 moles per decimeter cube, the expression for time dependent behavior of concentration of NO in moles per decimeter cube is. Very nice question. Easy but a bit tricky. Option A, 2 times 1 minus e to the power minus kt. Option B, 0.5 times 1 minus e to the power minus kt. Option C, 1 minus e to the power minus kt. Option D, 1 plus e to the power minus kt. It's very easy. Please pause the video. You can solve this only if the concept is understood. Pause the video. Try. Okay. So see what is given. It is given that N2O2 in gaseous state becomes 2NO. Correct. So by looking at the reaction, we can write the theoretical rate. What is the theoretical rate? Minus concentration changes of the reactant with time is equal to 1 by 2 dNO by dt. This we can write, correct. And we want to know the concentration behavior, time-dependent behavior of NO. NO is what we want to know. And by just looking at the question, you can see that there is a term of exponential in it. It is said that it is a first order reaction. Correct. And we also know that which equation does have exponential term in it. That also you know. A is equal to E naught e to the power minus kt. So we'll need to use this as well. Okay. But how? So for that, we have to understand that. Let's say that initially it is said that this is 1 mole per decimeter cube. Okay, whatever unit it is 1. And product won't be formed. After some time, some amount of the reactant will react. It will be consumed X amount. And based on the stoichiometry, this will become 2X. So the amount of NO which is formed after a time interval of T is going to be 2X. And we don't know what X is. We need to find X, that's all. We need to find X, that's all. So we'll start with this. Okay, we already know that A is equal to initial concentration into e to the power minus kT. What is A? A is the final concentration. A naught is the initial concentration of the reactant. Correct? This is A giving P. And we know that this is the initial concentration, X is the amount reacted, and A is the final concentration. So I can write the same thing as 1 minus X is equal to initial concentration is 1 e to the power minus kT. Or if I rearrange, if I bring e to the power minus kT to this side, 1 minus e to the power minus kT is equal to X. That's it. What do we want? We want NO. How much of NO is formed? 2X. 2X amount is formed. We know X. So amount of NO formed after a time interval T is 2X, which is 2 times 1 minus e to the power minus kT. And the correct answer is option A. A, na? Yeah, A. Very easy. Very, very easy. Okay. All right, so with this, we'll wind up the session of first order kinetics. We have come to an end. So I'll discuss the question in the next session, question number 16. Carefully do the question, do not end up making mistakes. Focus. Read the question at least twice. Write down the equation. Okay. Chalo. Okay. So see you in the next session. Bye-bye.